All right. Uh, Probability lecture part two, discussing the fundamentals of probability. So we talked about counting. Now we need to get into how those methods of counting help us turn these values into probability. So a couple things. First of all, sample space. Some definitions that we need to identify. Sample space is all the possibilities that can occur from any given situation, any given event that we identify. We then divide, right, the number of possibilities that we're interested in over the entire sample space. So let's start with something easy. You're dealt one card from a standard 52 card deck. Find the probability of being dealt king, heart, king of hearts. So in case you're unfamiliar, 52 cards, there are 13 suits. Sorry, 4 suits. There are 4 suits and 13 of each of those suits. And those cards go ace to king. All right, ace, 2 to 10, jack, queen, king. So a single king, so basically there are 4 kings, one of each suit. So the probability of getting a king is 4 out of the total number of cards, 52. Now, a couple of notes. So I'm a big believer in probability statements because everything we've done, we always put our units on there whenever we have context. And so probabilities, by definition, it's just a number, right? 4 out of 52, whatever probability that would be. Like 8%. So the thing is that in order to actually identify that, all right, we need a statement to identify, because if you just say 8%, what does that 8% correspond to? That 8% is the probability of getting a king. And similarly, probability of getting a heart. Since there are 13 of each suit, there are 13 heart cards out of 52 total cards, which is 25%. And then lastly, the probability of getting the king of hearts, all right, is one of those. All right, there's only one of each card, 52 distinct cards in a deck out of 52. And again, this is what I was talking about. Perfectly fine to leave this as a fraction or a percentage. All right, in my math lab, it's very specific on what it wants, fraction, probability, or percent. But all right, and I try and specify that on the activities of how to enter the value. But most of the time, I was like, for the quizzes, write it however you want. I review all those quizzes by hand. All right, so I put eyes on each quiz. They're not auto-graded. Okay, an interesting application before we get into more problems with probability is genetics, because probability is just such a big application of genetics. And so let's look. And so, like, I mean, you may have already seen the eye color one with blue eyes and brown eyes and how that works. But just another example. The following example deals with cystic fibrosis, an inherent lung disease occurring in about 1 out of every 2,000 births among Caucasians and 1 out of every 250,000 births among non-Caucasians. Each person carries 2 genes that are related to the absence or presence of the disease, cystic fibrosis. Most Americans have the normal gene, which we denote by capital C, and unaffected by cystic fibrosis. However, 1 in 25 Americans have 1 normal and 1 defective gene. A person with 1 normal, 1 defective gene is known as a carrier, but usually not sick. And I say usually because genetics is actually much more complicated than we are making this out to be. So the whole idea of 2 parents are carriers, what's the probability their child will have cystic fibrosis? So if I have capital C, capital lowercase c on the first parent, capital C, lowercase c on the second parent, and then it breaks into these possibilities. Basically, right, the probability that you would get lowercase c, right, that is the child would have cystic fibrosis, that is one possibility out of the 4. Because the sample space in this case, there are 3 things that can happen. Big C, big C, big C, little c, big C, little c, and little c, little c. And those are all the possibilities, right? Same thing. The chance that the child is a carrier of the disease is 2 out of 4. And so it is an interesting concept of that is the absolute basics of genetics. All right. I have the Titanic data set here broken down. And a big thing, okay, once we start getting into numbers. So Titanic, I have this data set broken down into class, first, second, third, and crew, and survival, alive or dead. All right. Of the 2,201 people that were aboard the Titanic. When you have a 2-dimensional contingency table that looks like this, your absolute first step is to total the values. Now, good news for us, I've already done that for us. I summed all the values up. You sum across the rows, all right, getting that 711, that 1490. Then you sum across each column. And overall, those 2 values create what is known as the overall total, that 2201. These 2 numbers sum to that, and those 4 numbers sum to it, and they should be the same number, so it's a way to check yourself to make sure that you added that correctly. And then once I'm here, we can answer all kinds of questions about probabilities. But that is always your first step with a 2-dimensional table like this. And tables are so commonly occurring that you just have to know how to read them and then deal with the values. So what is the probability that a randomly selected passenger survived? So probability, all right, and we're going to call and then we can actually make some notation. Alive and not alive, all right? So when you have a variable with a line over it, we call that the not probability, all right? Now, you can just always write out, I mean, I could do this multiple ways. I could say probability of alive, or I can use my shorthand probability A. So that's really up to you, all right? But the big part is you need a probability statement, all right? Again, like I said, big believer in probability statements because it is the units of a probability. And you need to make sure you have your units, all right? Just writing out the decimal, all right? And I know that's how a lot of activity problems are going to be. I know that's how a lot of home fun problems are going to be. But when I have fill in the blank type questions, and you should practice it constantly on your own, all right? Make sure that you're writing a probability statement properly. Okay, so probability alive, and there are 711 people that survived out of 2201. What is the probability that a randomly selected passenger was in 3rd class? Probability 3rd. Again, whatever notation is helpful to you, that's what you want to emphasize. Probability 3rd, there's 706 people in 3rd class out of 2201. What is the probability a randomly selected passenger was in 3rd class and survived? Probability 3rd and alive. Notice that now I'm using a connector word in there. We're only going to focus on a few connecting words and, or, and conditional. All right. But otherwise, mostly what we are doing is we are finding single probabilities or 2 joint probabilities. And that's pretty much it. Okay, 3rd and alive. So 3rd and alive, there were 178 of those people out of everybody. 2201. What is the probability that a randomly selected 3rd class passenger survived? Okay, so now this is a conditional probability. It is a given. All right, and this is where it starts to get interesting, because notice the difference in the questions here. Randomly selected passenger in part C, randomly selected third class passenger. That means, right, of third, what's the probability they were alive? And I could also write this as probability of alive given third. And that's typically how we write it. All right, and we're going to talk about shorthand notation in a bit. So that means only of the third class passengers. That means only of these people. So, all right, people who were in third and alive was 178, but only out of the third class passengers, that becomes 706. So 178 out of 706. What is the probability a randomly selected survived passenger was in third class? Now, this is the same thing, but in reverse. Randomly selected survived passenger. So that means given they were alive, probability they were in third class. So that means out of those who lived, of those that were alive, we have 711 of them. All right. How many of those were in third class? 178 out of 711. And so notice, all right, these three problems, the numerator on all three of those is 178. The denominator changed each time based on the wording of the question. And that is the trick of probability. It's all about the subtlety of the wording. So that's definitely what we're going to put our focus into. The following table refers to a survey of senior high school students in Laramie. Students were asked whether they had ever smoked cigarettes and whether they had ever had alcohol. All right, we see a chart here: drank, never drank, smoked, never smoked, and then a bunch of questions. So, like I said before, our absolute first step is to do the totals. Before I even bother reading the question, all right, I need the totals. $27, 1949, 781, 1495. Summing those together gets me 2276. So that is our absolute first question before you even bother reading anything else. And again, you can always write it out as drank, never drank, smoked, never smoked when you do your probability statements, but it's just nice to use shorthand notation. Drank, and then did not drink, smoked, and then did not smoke. So that bar represents did and then not did, right? So drank, not drank, smoked, not smoked. So that shorthand notation is really, really nice for us. Okay, what is the probability that a randomly selected student drank alcohol or has never smoked? Probability, drank, or, and again, I know this is an or problem because it says or. And like I said, there was only three connectors we were going to talk about: given, and or. And it's straight in the question. And has never smoked, drank, or did not smoke. So or is actually a kind of a complicated question. All right, because when we look at this, we need to look at the people who smoked or drank or did both. And or is inclusive. All right, that's a big one. All right, did one or the other or both. So, all right, those people that drank, they drank or never smoked. Those people drank or never smoked. All right, those people drank or never smoked. So actually, it's all three of those categories. The only people here that don't count are those ones because they smoked or never drank. And actually, those are the only ones that are excluded in this category. And this is out of everyone, 2276, which then gives us 2230 out of 2276, 98%. What is the probability that a randomly selected student has never smoked? Oh, good. Well, we already have that one. Never smoked. That's just the total here. So 1949 out of 2276, which gets us 86%. If a student has drunk alcohol, unfortunately, that is grammatically correct, even though it sounds horrific. What is the probability the student has never smoked? This is a conditional again. All right, probability. All right, never smoked given drank. All right, so that means I'm only looking, all right, I'm basically covering up everyone who did not drink. So I'm only looking at this singular column here. All right, that's all I'm looking at. So I have a total of 781 people. Then I look within that column of those 781 people who never smoked. Oh, it's that 500. And so hence it is 500 out of 781. 64%. And lastly, suppose a student has never smoked. What is the probability the student has drunk alcohol? Now, this is another given. Now, notice that, okay, I know these are givens because one, they lack the word and, they lack the word or. Additionally, they're saying something happened first. Suppose the student never smoked. If a student drank, right? If those things happen first, that's what identifies it's a conditional. Right? So, given, never smoked, probability, drank. So drank, given, never smoked. And again, we look at the conditional first. Never smoked, which means I'm looking only at these values here. Then I look of those people who drank. So there were 1,949 people. 500 of those never drank. Or did drink, sorry. Which gives us 26%. And again, just over and over, the best thing to do, just keep practicing reading the problems. All right, so now back to permutations and combinations. All right, when dealing with permutations and combinations, we do everything that we were doing before. You count the number of ways something happens, and then you just end up with permutations and combinations in both the numerator and the denominator. That's basically what creates a probability. It's an extension of the counting stuff that we did. So a club consists of 5 men, 7 women. 3 members are selected at random to attend a conference. Find the probability the selected group consists of 3 men or 1 man, 2 women. So we're creating a group, which means looks like no repeats. And then also looks like no order. So this is a combination. So with a combination, all right, in order to find the probability, 3 men. Okay, so let's do the denominator first because that's going to be simpler. We are selecting 3 people from a group, a total group of 12 people. That means in the denominator, I have 12 NCR 3. In the numerator, this is like the counting we were doing for our junior senior council members. All right. I have 5 men. I'm selecting 3 of them. And then of the 7 women, I'm selecting 0. And that gets me the probability, right? And remember, 7 NCR 0, that's just 1. And that would actually get me the probability, which would be 0.05. If I want 1 man and 2 women, the denominator is going to be the same, still 12 NCR 3. And then of the 5 men, I'm selecting 1. And of the 7 women, I'm selecting 2. And that gets us 48%. So again, just very similar to our counting techniques. In order to make probabilities, we have the possibilities that we're interested in divided by the total possibilities. In drawing 5 cards from a 52 card deck without replacement, what is the probability of getting 5 spades? All right. Basically, whenever dealing with cards, 52 card, our standard 52 card deck, that is. All right. That's always a combination. Probability 5 spades. In the denominator, we actually already calculated this one. I have 52 NCR 5, and I know that's like 2.5-ish plus million. All right, then in the numerator. Okay, so 5 spades. So remember we talked, there were 13 of each of the 4 suits, which means that picking just that one suit, there are 13 spades, and I want to select 5 of those. And then I could add the other, remember, there would then be 39 cards remaining, and I'm getting 0 of those. Now, again, remember that that is just 1, so you can leave that off, all right? Like, I just put it there because the 2 first numbers, 13 plus 39, have to equal 52, and the 2 second numbers, 5 plus 0, have to equal 5. And then that would get a probability of 0.0005. All right. So probability is a concept in statistics, and everything in statistics is all about pictures. Pictures are worth 1,000 words, right? They help us describe what is happening. And so the Venn diagram is a massively helpful picture that we like to create. And it's going to show us what's known as the general addition rule. All right, both the specific and the general addition rule. All right, because a Venn diagram visually displays probabilities of events. So we have 2 cases: disjoint events and overlapping events. And a Venn diagram is just a box with 2 circles in it. Depending upon the case, those circles either overlap or do not overlap. So in the disjoint case, and notice the wording disjoint, not connected, right, is what that means. If I was, this is things that do not overlap. For example, your grades at the end of the semester, right? I cannot get both an A and a B in a course. So those are disjoint events, right? Grades, final grades, all right, are disjoint. Things that are overlapping is something like, I would like cream or sugar in my coffee, or both, right? And so you have an overlapping case here, right? This middle probability here, this middle piece of this overlapping picture, that would be cream and sugar in my coffee. Can I have that? Yes. All right. So there's lots of situations of both of these, and it's really going to be context, right? As you read the problem, all right, can they occur together or not? They end up with two different probabilities for finding the or. In the disjoint case, it's simply, if I'm looking for A or B, I add the two together. In the overlapping case, you add the two together, but when you add the probability of A plus the probability of B, the middle piece got counted twice, which is why in the equation you subtract it out. By definition, or in mathematical language means add, but add doesn't just mean adding positive numbers, right? I'm adding two values and subtracting one. That is, I'm adding a negative. All right. So it depends on what is happening in the picture, dependent upon which formula you use. You have two options. All right. The complement. So this is that notation that I was talking about, not. Okay. So if I have the event A, the complement of A, we write it as A naught or AC. I like the A naught because the A with the bar over it, because it's just very fast to write. And so for our Venn diagram, just to see a picture of that, if I have the events A and B and they're overlapping, and then I want to find the complement of A. So that is everything not A. So if we're doing our cream and sugar example, so if the event A is cream, that means I want my coffee, all right, with either only sugar or black. And basically that's what is remaining after I look at everything that is not A. That doesn't even include, right? Because this middle piece here, that's cream and sugar. And it's not that. That is not A. Basically, right? I do not want cream, or I can't even remember. A was cream. All right. I do not want cream in my coffee. All right, let's look at an example. Suppose that 90% of students at Gillette have a cell phone, 36% have an iPod, and 30% have both a cell phone and an iPod. What is the probability that a randomly selected Gillette student has? And then we have a bunch of questions. So the primary idea here is, before I even bother with the questions, I draw a picture. Identify my information and then draw a picture. So suppose 90% of Gillette students have a cell phone. C for cell phone. 36% have an iPod. 30% have both a cell phone and an iPod. Now notice this one already says and, which means I already know the picture I'm going to make. That is the overlapping picture, because you can have both a cell phone and an iPod. Now comes the actual part where we put in the details. Now, you may already notice something looks weird here. 90, 30, 36, those values are over 100%. So what's better than one picture? I like to draw two pictures. This one is called the half moon pick. And it is the same information. This middle one is still C and I, and that is still 30%. But now I want to look at the things more individualized. If I cut everyone who has both a cell phone and an iPod out of cell phone, that leaves just cell phone or cell phone and no iPod. Basically, and then in order to calculate that, 90% of people have cell phone, 30% have both. So that's 90 minus 30. That makes this 60%. Similarly, I can do that on the other side. No C and I, and that's 6%. Now notice the nice thing about this bottom picture. 60 plus 30 plus 6, that's 96%, which means I can identify what the outside probability is. 60 plus 30 plus 6 is 96, which means we have 4% of people on the outside. And who are those 4% of people? Those are the people who do not have a cell phone and do not have an iPod. Now, the good news, that outside is the same as the outside on the top picture. And this is the nice thing about statistics, that I can do most of my work without formulas at all, because I can make pictures and logic almost everything out. All right. I don't need any formulas. We have a couple. All right. But we barely use them because I identified everything with just simple addition, subtraction, and logic. Now watch. So, right, we were looking for, what is the probability a Gillette student has a cell phone or an iPod? Probability C or I? Well, I can use this formula above. Probability C or I equals probability of C plus probability of I minus the probability of C and I. That's the general addition rule from above, which gets me 0.9 plus 0.36 minus 0.30, which equals 0.96. But wait a second. That's the summation of those three numbers that I found right there. And that's the really, really nice thing about drawing the pictures. So I can just say, oh, 0.96, like, because I can just look at the pictures. Also, look at this. Neither a cell phone nor an iPod. Probability, no cell phone and no iPod. We already found that number too. Probability a cell phone, but, which is another fancy word for and, no iPod. And oh, look, cell phone and no iPod is that guy that I found right there. So if you make the pictures, you can save yourself a lot of frustration, all right, in trying to calculate. The biggest problem I see is people skip past the pictures, immediately go to the question, then they're like, oh, I don't know what to do. Take your time, set up the pictures, identify absolutely everything you can, label everything well, and the problem flows very, very smoothly. All right, odds. If the odds of an event is A to B, all right, A colon B, then the probability of that event is A all over the summation of A and B. Odds is something that you should be at least semi-familiar with, because odds and probability really go hand in hand. The difference is really just how you discuss the probability. So odds, right? So the odds of rolling a 4 on a fair, normal 6-sided die, right? So it didn't specify, but we are talking about a regular die. So we know the probability of getting a 4 is 1 out of 6, right? numbers 1, 2, 3, 4, 5, 6. There's 1, 4 out of 6 possibilities. That's 1 out of 6. So probability, you're probably more familiar with. Odds are read as for to against. All right. When you're talking about odds for, you can also say odds against, and then you just flip them the other way. So there is one chance I have a 4, and then there are 5 other sides of the die I do not have a 4. Notice those two numbers together sum the denominator 6. And that's how odds work. So odds are actually very, very simple. But people really confuse themselves with them. Start with the probability because that's what almost everyone is much more familiar with. And then from the probability, identify the odds. Let's look at an example. The winner of a raffle will receive a 2-year scholarship to the college of his or her choice. If 1,000 raffle tickets were sold and you purchased 5 tickets, what are the odds against your winning the scholarship? So let's start with probability of winning. I purchased 5 tickets. There are 1,000 total tickets. Odds is the one thing. So note, you may have noticed I don't reduce, I don't turn it into probabilities, because it's all the same to me. The concept is done at that point. The details only matter what the question asks for. Odds, though, you need to always reduce. So that reduces to 1 in 200. So in order to do odds, I always start with odds for the event. Odds for the event, there is one chance that I win and 199 chances I do not win. Remember that these two numbers, 1 plus 199, sum the denominator. Okay? And so then, but we were actually looking for odds against. So in order to do odds against, all you have to do is flip it. That then becomes 199 to 1. And that's what we're actually looking for. From a survey involving 1,000 people in a certain city, it was found that 500 people had tried a brand of Diet Cola, 600 tried a certain brand of regular, and 200 had tried both. A resident of the city is selected at random. What is the probability? And I put the word empirical in there just because probabilities are about long run chance of an event occurring. And so empirical means, right, the probability something is supposed to happen in the long run. For example, when you flip a coin, there's a 50% chance I get ahead. However, I can flip a coin 100 times and I can get 100 tails in a row. That is not long run. I can get 1,000 tails in a row. However, in the long run, it is 50% heads, 50% tails. Okay, where was it? What is the empirical probability that the resident has tried diet or regular? So just like everything, start with a picture. And just like before, I'm going to actually write both pictures. And I know this is overlapping because it said both, right? When it says both, then I know I have an overlapping probability. Okay, so let's see. We have regular. And since these are basically probabilities that we were given because they're all over 1,000. So let's see, 600 out of, so 0.6. Diet is 0.5 and regular and diet is 0.20. And again, I don't like to make just one picture. I like to make 2. because basically if you make both pictures, I have no calculations to do after I set all this up. So regular and diet is still 0.2. And then I have regular and no diet and no regular and diet. And notice, label your graph well. Laziness in the labeling is where I see the most confusion. All right. If you only make one picture, and a lot of people, they jump straight to this picture, all right, label it poorly, and then miss all the questions. Make both pictures, label everything well, all right? Okay, so 0.6 minus 0.2, so that means this is 0.40, and then 0.2 minus 0.5 is 0.30. And then I know the outside, which is not regular and not diet, which is, let's see, what are we at? 60, 70, 10%. And that creates 100%, right? The whole point is these values all together, they have to be 100%. These values won't be. A lot of times these are over 100% already, as we could see. 6, 20, 50. I mean, that's over 100%. These values together sum 100%. Okay, now back to our question. Probability that a resident has tried diet or regular. Probability diet or regular, which means that is the summation of these three values, which is 90%. What are the odds for this event? So 90%, which is 9 out of 10. So the odds for, there are 9 chances that does happen. And then remember that 9 plus some number must make 10, which means there's 1 chance that does not happen. So 9 to 1. What is the probability that the resident has tried one of the colas, but not both? All right. There is no great probability statement for this with our notation because, I mean, I can write it, but it's kind of ugly. Only one, but not both, means I'm looking at this or this, but not the middle piece. Or, all right, in statistics is inclusive, all right? But here, it's only talking about that one or that one, which means that value is 70%. So it is the, I'll write this out. So it's probability of R and not D plus the probability of not R and D, which is the 0.4 plus 0.3, which is 70%. So that one is important, but again, it was nice I had my picture, but knowing what that was, I had to look specifically for what I was trying to identify. And what are the odds against this event? So again, I'm going to start with odds for. There are 7 chances this does happen, and then hence 7 plus what number makes 10? 3 chances that does not. And so hence the odds against are flip that, 3 to 7. And so I like to always identify odds for first, and then you just flip those to identify odds against. All right, we will leave it there for now. and pick that up next lecture. Have yourselves a wonderful day.